Good evening, my dear classmates and professor. My name is Jun Feng, and welcome to hear my presentation of my EE591 project. And my project topic is MRI T2 mapping in knee cartilage. So for the goals of my project, the first goal is design a Voxel-based T2 mapping algorithm for knee cartilage by using least square estimation method. And the second goal is adding Gaussian white noise into simulated input images, and then figure out M0 and T2 SNR value and determine SNR optimal TE. So here, the simulated input images are the imaging at different TE, which are calculated by the result of the goal 1. And about the uniqueness, I did this project exclusively for EE591. So let me talk about the motivation here. Nowadays, for some knee cartilage disease, like osteoarthritis, the physician needs some specific physical signs to diagnose, like the stiffness and the swelling degree in knee joints. And for MRI imaging, the T2 differentiation between normal and abnormal knee cartilage indicates the severe degree of this physical signs, which is useful for the further diagnosis. So here are the other existing MRI solution. We can see there are some solution for evaluating cartilage physiology, like the ultra-short echo-time imaging. But right now I want to talk about the T2 mapping specifically. So here is the method for my project. The basic formula is the T2 relaxation formula, which is the imaging equal to M0 map times the exponential of minus T corresponding TE over T2 map. And the M0 map here is the mechanization after RF excitation. And here, I use the least square estimation to estimate T2 map and M0 map, since the noise in the imaging is independently and identically distributed. And for MATLAB function, I choose the least square curve fit function for nonlinear least square estimation. And here is the description of this MATLAB function. Okay, for details, the method of Voxel-based T2 mapping. The first step is loading the knee cartilage MRI data, and then calculate the starting point S0, which contain the M0 knot map and T2 knot map by using basic formula. And then set all the TE for S data and corresponding imaging for Y data. And the fourth step is use the least square curve fit function to calculate the final T2 maps and M0 map results and print out the tracking plot. And the final step is use the overlay algorithm to generate the T2 map onto the knee anatomy MRI imaging. And for the methods of M0 and T2 SNR value calculation, the first step is use the final T2 map and M0 map result I just mentioned before to get the simulated imaging at different TE moments. And then add the Gaussian white noise into this imaging. The equation of Gaussian white noise is like this. And the third step is use the same program to calculate the T2 map in white noise and M0 map in white noise. And the final step is use the MATLAB SNR function to calculate the M0 and T2 SNR value. Okay, so let me talk about the result for the Voxel-based T2 mapping. And so here is the M0 map and T2 map at the starting point. And here is the signal TE plot, the tracking plot. In the tracking plot, the blue dots here are the Voxel-based mechanization at different TE coming from the X data and Y data. And the line here is the T2 realization curve. This signal TE plot show that the least square estimation do work. And these are the M0 map and T2 map after the least square estimation. So we can see that the average T2 value for the T2 map is around 30 to 40 milliseconds. And also this is the T2 mapping overlay on the anatomic imaging. So here I want to mention that the data provider here has the normal knee cartilage. So that means the T2 values in the T2 map from my program are close to the T2 value which belong to the normal cartilage, as one paper indicates. So this is the paper. And for this sentence, we can see that the normal knee cartilage T2 time is around 40 milliseconds. And here is the result of T2 map checking. Compared to the reference T2 map created by a software called MRMap, we can check the results of by voxel. So here you can check that the T2 value at this point are 31. Also here are 31. And also for the T2 value at this point are 25. And also here is 25. And here for the result of the M0 and T2 SNR calculation, we can see that the signal TE plot is still like the same as before, which means that the least square estimation does work. And the final M0 map and T2 map are similar to the those maps without white noise. So here I want to show you some form about the SNR. So for when the sigma is equal to 10, the standard deviation equal to 10, the T2 SNR optimal TE should be 20 ms because the T2 SNR is the biggest. And for when the sigma equal to 25, the optimal TE should be 10 ms because the T2 SNR is the biggest here. And here I want to mention that it seems the sigma will have some sort of effect to optimal TE. It seems the larger sigma cause smaller optimal TE. So here is the conclusion. Point one is that according to the reference T2 map, the results coming from this T2 mapping program are correct. And the second is the T2 values from this program indicates that the data provider actually have the normal knee cartilage. And the first point is that for the M0 and T2 SNR calculation, the result indicate that with the increasing TE, the M0 SNR is already decreasing. However, the T2 SNR is increasing to a peak value firstly and then decreasing. Also, the sigma has some sort of effects to TE2 SNR optimal TE value. So here is the challenge. The first is that I only got the control group data with normal knee cartilage, lack of patient data with abnormal knee cartilage. And the second is I didn't figure out the principle of the M0 SNR and T2 SNR variation pattern within the increasing TE. And here is the lesson I learned. From my project, I confirmed that the voxel-based T2 mapping technique is sensitive to the collision matrix, bone, and water content. So here is the map. When I select the bone material a little bit, so the T2 of the bone shows the red dot, which is sensitive. And there's other implementation method for Voxel basis T2 mapping besides the least square estimation. And thank you to hear my presentation. Thank you.